If y'all are ready, we'll go ahead and get started with the introduction for today's speaker. Before we get too far down the road, please turn your phones to vibrate. I know you have something very important to hear about, but it can hang on for an hour. So it's my pleasure to introduce Don Boesch. Don has a storied record in the field of marine sciences going back to at least the 70s when I first met him in Texas, and he was at Virginia Institute of Marine Sciences, and we were working on what were then Bureau of Land Management projects as oil and gas was developing on our continental shelves, and they were attempting to develop an inventory. Don's from the South, born in New Orleans, went to Tulane University. I have his very first community ecology analysis book he wrote for the EPA back when we did multivariate by hand. It was a pretty painful experience in those days. Regina sent around his introductions already for you a little while ago, so I'm not going to carry this out any longer and just introduce Don. He's talking about restoring Chesapeake Bay water quality while factoring in climate change.
Thanks, John. Can you hear me with this as well, or is it better with this?
You're going to stay at the podium. You can use that one, so you turn it on down there at the bottom.
Oh, it has to be turned on. That's why you...
Yeah, I got a bigger button. There you go. Touch that one.
There you go. Okay. I might need that if I walk away. So
It's on standby then.
stand by.
Just
Good.
touch it once.
Good. Thank you so much. Well, it's really a pleasure to be here at the Sea Lab. I can't remember for sure. I think this is my fourth visit here over the many years. But it's been a long time until I came just a couple of years ago with the National Academy's Gulf Research Program Committee. And it's always good to visit a marine lab, and it's particularly on the Gulf Coast. So one of the things, before I get into the talk that I want to give today, that I'm here to do is to begin the process of, after I step down from my long administrative service in Maryland, to write a book. And the book I want to write is about the Gulf of Mexico and science, things that you're all interested in. Hopefully you'll buy my book when it comes out. But when I was putting these ideas together, anticipating my stepping down and having the time to do it, last year another book came out, and when I saw it I said, oh God, this guy stole my idea. And it's a book by Jack Davis. It's called The Gulf, The Making of an American Sea. Davis is an environmental historian, so he tells it from a human perspective in terms of human development of the Gulf of Mexico area. It's an excellent book, and the reason I grabbed it here to have it here today is to tell you yesterday this book won a Pulitzer Prize. So if you haven't read it, and you should read it because it tells you some things that we won't really know about, even if you worked here. I was mentioning earlier that did you know that the snapper, overfishing of red snapper, is a problem that actually already was manifest in the 19th century? Things of that sort. So it's in this good book. So hopefully I'll still have some important things to say that Jack Davis, or take a different slant at it. So when I thought about what I could tell you about today, it's something I've been involved in fairly directly, not in the form of actively doing the research myself, but as someone who is responsible for communicating our science and making sure that we're using good science to move forth in public policy, is the long adventure we've been under to restore the water quality in the Chesapeake Bay, where I've worked for over 38 years of my career. And in addition to that, while you're dealing with that problem, then comes the fact that the world is changing, the climate is changing. And I thought you'd appreciate this because here, maybe it's difficult to talk about here in coastal Alabama, but in the Chesapeake now we can't avoid having to address the issues of climate change because it's now become pretty evident in public policy in at least some of the states in the Chesapeake Bay region. Does this have to be turned on as well? I don't think it is. Where's the switch? No problem. Thank you. Thank you. That is still not working. While we figure that, let me do it the old-fashioned way.
Spacebar or?
Nothing is working.
Hold on, I know what it is. Now this will work.
Okay, great. Now, here we're in business. So, first of all, the introduction to the Chesapeake Bay. You've all heard about it. You've heard about it in many ways because a lot of research is done there. You're probably familiar with the research paper. You're also probably, or like a lot of places, colleagues elsewhere in the country, envious because you think all the research money in the world goes to the Chesapeake Bay and it doesn't come down to here. First of all, that's not that's not true. People work hard, scientists work hard to bring research money to the Bay, and secondly, it is true that this area has received a lot of attention from coastal scientists over the years, and for good reasons. It's a important water body, the largest estuary in the United States. And it's historically and culturally important in so many other ways, economically important. But in the 70s, it became evident that the bay had changed rather dramatically over the years. Earlier, it was thought that the bay had some spots where the quality, industrial harbors where the quality wasn't great. Certainly had overfishing of things like oysters, but generally the bay was in good health. And then it became apparent that wasn't the case, and the bay had systemic problems manifest in the fairly dramatic loss of much of the seagrasses that are in the shallows of the bay, degraded water clarity, and persistent, recurrent seasonal hypoxia in bottom waters, the classic symptoms of a system that's over-enriched with runoff and inputs of nutrients into the system. So I'll tell you the history of the policy in just a minute, but let's just talk about this bay to begin with. First of all, it is a large water body. It's 300 from the mouth up to where the Susquehanna River dumps into the upper end of the bay. It's 320 kilometers, and it's expansive. You can't see across the lower part of the bay, but it is relatively shallow. So the depth, not by Gulf Coast standards, but by world standards, its average depth is only 7 meters deep. So if we think then of the volume of the bay and the vast watershed, in this case 166,000 square kilometers of catchment area that drains into this system, this makes it very susceptible to inputs from the watershed, particularly in the form of nitrogen and phosphorus, but also sediments from this vast watershed into comparatively a small volume of water. And because the tides are modest at best, ranging from about less than a meter at the mouth to maybe just a foot in the upper parts of the bay, it doesn't get a lot of tidal flushing. So as a result of that, the residence time of water, and when it enters the bay, say freshwater molecule, water molecule when it enters the bay, is about half a year. So this makes it, again, susceptible to these inputs from the vast watershed. And you can see also that the watershed expands over 6 states and the District of Columbia, including not only Maryland and Virginia, which we all think of the Chesapeake Bay states, but also half of the watershed is the catchment is in Pennsylvania, extending up into New York State and West Virginia and Delaware. Well, so when it was recognized in the 70s that the bay had some problems, the governments, the state governments and the federal government got together developed this agreement. And the agreement, the first agreement in 1983, said nothing more than we're going to improve the health of the bay. It didn't have any specific objectives and goals, but we were focusing then on the problem of this nutrient over-enrichment issue. So by 1987, the agreement was amended to include specific nutrient reduction goals of 40% reduction in nitrogen and 40% reduction in phosphorus loads to the bay, with the objective is that we were going to achieve that in 13 years. By 2000, we would have done the job. Well, 2000 came along, and we hadn't even made a dent in it. We saw no real improvement, and the best estimates of the reductions in the load were a very fraction of the 40% that was intended. One of the problems is that we were doing this through a lot of voluntary commitments. The states would say, we're going to be good boys and girls, and we're going to reduce our emissions, reduce our inputs, but we weren't using basically voluntary approaches. And this is particularly important with respect to agriculture, which is a dominant source, as we'll see, one of the largest sources of nutrients into the system. But even wastewater treatments, there were no specific mandates that were included at that time. But in 2000, they said, I tell you what, we're so serious about it this time. By 2010, if we don't meet the goals, we will agree that we will put into a mandatory requirement that will require the states to take specific actions to reduce those loads. Under the Clean Water Act, there's a provision called total maximum daily loads, where if you take all of the things you're trying to do with regulating wastewater inputs from point sources, from stormwater inputs and so on, if you're not successful in achieving the water quality standards, then it's incumbent on the responsible party, the states in this case, to take action to reduce loads to a total maximum that you can calculate that the system can handle and still meet those water quality objectives. Now, there are TMDL plans for probably, I dare say, there are those here as well, from all water bodies all over the country. But the EPA has, under any administration, has failed to actually often require that they be enforced. And so the Chesapeake case is one where they actually entered into an agreement, a binding agreement with the states and the EPA to actually require it. This was immediately, as soon as it came out, the 2014 action plan, which had these commitments in it, immediately challenged by our friends in the American Farm Bureau Federation, the Fertilizer Institute. You know, those organizations don't have a vested interest in the outcome to challenge the legality of this under the law. And the federal court ruled against the plaintiffs, against the Farm Bureau et al. Massively. It was appealed. It went to the appeals court in the northeast area in Pennsylvania, and the appeals court again strongly upheld the decision, the action, because indeed the states had all agreed to it as well. It wasn't seen as just a federal imposition. So this was then challenged again for it to be brought to the Supreme Court. Supreme Court, remember a couple of years ago when we were worried about the delicate balance in the membership of the Supreme Court, and we had a Supreme Court member who died, and it looked like it was a 50-50 split. The Supreme Court basically decided not to hear the case. So it has legal standing as of this date. The industry, the ag industry, why did the ag industry challenge this? Are they really that worried about agriculture in the Chesapeake Bay? Not really. It's important to the region, but it's not a massive part of American agriculture. They were concerned that this would set a precedent, whereas other regions that have agricultural source inputs would also come under mandatory requirements to reduce nutrient loads. So where are we in terms of achieving this objective? So if we look at the These are simple bar charts, and it shows you the sources of the inputs that were estimated to be in 1985. You can see agriculture was the largest source, followed by wastewater inputs. There are then about 15 million people live in this area. There are now about 20 million people. So they have population centers which have large waste treatment facilities, as well as smaller communities. The interesting part, this is from forest. This was seen just from forested environments, what runs off from there. Mainly natural, but maybe also influenced a bit by atmospheric deposition. Actually, atmospheric inputs, this is from fallout from combustion of fossil fuels, for the most part, of oxides of nitrogen. Fallout on the landscape contribute nitrogen that goes into the bay. This is for nitrogen. There are similar graphs I could show you for phosphorus. So you can see where we are. It was estimated to be that we've made substantial reductions, probably in terms of where we need to be to meet the TMDL by 1985. We're probably, according to this estimate, reduced about 2/3 of the load that we need to. So we have the last third to go. Now, having said that, these are estimates based for the non-point sources from the diffuse sources where we can't actually measure them very well. These are based on computer models, which do make a number of assumptions, like there is no lag time. In other words, you can put a practice in and there's delay in nitrogens in groundwater. A recent paper in Science just last week said it could be 30 years before the if agriculture was able to reduce nutrients in the Mississippi Basin, before you'd see that in terms of reduced loads to reduce the size of the dead zone in the Gulf of Mexico. So there's a lag time involved in that. There's other assumptions about the efficacy of management practices. There are other assumptions about the implementation of those practices and so on built into this. But this is where we think we are. And so the challenge is that we've really milked out of the reductions. We've done this largely on the backs of wastewater treatment. You can see the reduction in size, and in reduction of atmospheric inputs. In agriculture, we've had some reduction, but again, this is somewhat questionable because it's not directly measured. It's estimated through these computer models. And we have, on the other hand, an expansion of urban runoff inputs because our cities are growing. Developed areas are being paved over and faster than the population growth, actually. And so that's hard to keep up with respect to the fact that we have these urban runoff inputs into the system. So those are the challenges going forward. Agriculture, let's make the final necessary reductions for agriculture as well as the urban sources. So, first of all, this is, despite the disparaging words I said about the model estimates, fact of the matter is now in recent years we're actually seeing tangible, documented evidence of improvements of the system in the bay, in the estuary itself, that scientists said would happen if we were successful in reducing the pollution loads. So this is information on hypoxia. You can see the area of anoxic volume in the channel, deep channel of the Chesapeake Bay varies widely from year to year. That's because it's influenced heavily by the amount of runoff, just like your river here. If you get a wet year, you got more fresh water, more nutrients coming into the system, more stratification of the estuary during those years that contributes to hypoxia. But if you normalize this from flow, we can see that this is the hypoxic volume, anoxic or hypoxic. Anyway, I think this is anoxic volume, time average. So this was in a volume per day, okay, over the summer period when this occurs. So it encapsulates both the extent of hypoxia, the volume of hypoxia, as well as the duration. We can see that that's on the steady decline. So in 2016 and also in 2017, we had almost no anoxia in the bay. That is, areas where there's no oxygen. Okay. The other leading indicator of this if you look at here is the data, or the data average for DO levels that we talked about here. But you can also look at this interesting pattern of a decline in bottom waters in nitrate, in ammonia concentrations, and an increase in nitrate concentrations. What this is showing us is that the nutrients, the nitrogen that's being recycled by degradation in bottom waters and in bottom sediments, the metabolic product is ammonium, and then that can be nitrified with oxygen availability into nitrate. So we're seeing less ammonium because that flux is being oxidized because of the availability of oxygen or nitrified to see more higher concentrations of nitrate. Another very clear indicator that the system is changing back in the direction we wanted. Another positive result published just a few weeks ago, is this by John Levchuk and his mentor Bob Orth and a bunch of other colleagues, showing the recovery of submerged grasses. In the Chesapeake Bay, we have a variety of seagrasses ranging from Zostera in the lower parts of the estuary, a fairly saline, requires higher salinity, to a whole series of other vegetation species up the estuary. So, and those are broken down by salinity zones. So we have the highest salinity, the polyhaline salinity, mesohaline, oligohaline, and tidal fresh water. What we can see is that the acreage, the area of submerged vegetation has been increasing since, again, 2 more years on this. It's continuing to go up dramatically. So the area covered by these submerged vegetation is increasing. From to 2015, more than doubled, and it's increased even more than that, as I said. But it's evident in most of the salinity zones except the lowest one, the polyhaline one. So on one level, if you think you're reducing nutrient sources from the head of an estuary, you would think that maybe you would expect a recovery, kind of moving upstream, but it seems not to be the case. The recovery in the lower salinity areas is the most impressive. The reason that you see delayed recovery or little recovery in the higher salinity areas, the polyhene areas where there's Zostera present, is related to the other part of this topic, that is climate change, because this is a northern species. It's close to the southern edge of its range, and it has real problems during hot summer conditions. The grasses tend to die off if you leaving a viable rhizome, but if you have multiple successive heat stress periods, summers, then the large areas of Zostera could be lost. Oh, backing up a little bit, I should show you this. You're proud of the history of the Dauphin Island Lab, and so you should be. We're especially proud of one of my laboratories, the Chesapeake Biological Lab, because it was the first laboratory of this kind that we have here on the East Coast, founded in 1925. So here is the Solomon's Island, not the one in the Pacific. This is Solomon's Island, Maryland. And you can see when shortly after the lab was formed, 1933, it was surrounded by fairly lush grass beds, clear water in this case. By 1963, mentioned, I think, we started to notice they started to go haywire around the 70s. There was much less expansive amount of grasses, but still healthy grass beds. And by 1999, there were none. So also as a symbol of hope, this year, for the first time since the 1970s, early 1970s, small shoots of rupia grasses began to reappear in front of the lab after these years. So a hopeful sign. So one of the things, as I mentioned, I said this is about climate change as well. So how do we hold these gains, and how do we make these improvements when climate is changing? And so in a warmer world, in a world where there are other changes in the amount of runoff we get from the rivers, that could push us back, and so that we might see more degraded conditions as a result of it. So I wrote a couple of papers back around the 2007 timeframe where I was a clarion caller saying, pay attention to climate change. It really wasn't on the radar, at least in terms of bay restoration then. And so what happened was, as I said, be careful what you wish for, because now they're actually saying, well, Boesch said back in 2007 we ought to be doing this. And so now we're in this fast march to try to factor in a legal framework where we have these mandatory goals and objectives, climate change. How does that affect the goals that we set and have to meet by 2025, which is the now deadline for the TMDL process that we talked about? I won't go into this, but and I'll actually kind of look at it in more detail in the next slide. But if you think about it, climate change can affect this eutrophication problem in the bay. Manifests in this one example, and I talked about the seagrasses as one, but manifest in particular in this case in hypoxia. Why hypoxia? Because it is the hardest thing to try to fix with respect to this diet that we're trying to do of reducing nutrient loads. The thing that requires ratcheting down on nutrient inputs most dramatically is to get the not well oxygenated, but minimally oxygenated waters in the deep parts of the channel of the bay. So if we can achieve that, we can achieve a lot of the other things that aren't related to hypoxia. So let's just look at how these conditions will affect hypoxia in the Chesapeake Bay, and indeed elsewhere. First of all, temperature is increasing, and it will increase even more. And interestingly, that by this estimate, actually would have a beneficial effect, reducing the amount of hypoxia. Why? Because as the seasons become earlier, forest and actually agriculture is shown are more retentive of nutrients. We don't lose as much of nutrients if they have the longer growing season. On the other hand, if we looked at the water temperature in the bay itself, in the estuary itself, over here, that actually would exacerbate hypoxia. Why? Because first of all, estuarine water, even when it's saturated with oxygen, holds less oxygen. So it starts off with less oxygen to begin with, has faster metabolic rates of the microbes that degrade the organic matter to deplete the oxygen. So that one will drive in the other direction. On the landscape, the estimates are that we will have generally increased precipitation, maybe more of it coming in the winter and early spring, less in the summer, but also rainfall already is becoming more intense when it falls. So that means more runoff, if you will, particularly for something like phosphorus, which is tied up into the sediments and the soils, and that might cause more runoff, so that could exacerbate the problem. On the other hand, temperatures are warming, so there is evapotranspiration that takes some of that extra water that's in the water system and puts it back into the atmosphere before it gets into the bay. That has to be factored in. So the other things, so the expectation is that, and models would suggest that there's increased watershed flows and loads that are delivered to the bay that should exacerbate the situation. At the same time, the bay is filling up. Sea level is rising, so the bay is becoming, the volume of the bay is expanding, which on first principles you would think that might actually have a beneficial effect to the larger volume in which to degrade this organic matter. In addition to that, the result of that is that you have more water coming from the ocean, the mouth of the bay. Salty water, well oxygenated water comes up into the bottom layers of the bay, which could help ventilate the system. So the objective is, how does this affect the deep water hypoxia in the bay? First of all, let me convince you that climate change, I don't need to convince anyone that climate change is real, but in this audience, but let me convince you that we're actually seeing climate. It's not something in the future, it's something that we've been experiencing already. This is the salinity records. This is the value, John, of long-term observations made at the two piers of the two major research institutions in the Bay, the Chesapeake Biological Lab I already told you about, and this is the VIMS pier, down in Virginia. And both show this secular, obviously a lot of variation year to year. This is the mean annual temperature, a lot of variation year to year. Of course, we know that. Some years are warmer and some years are colder. But over the long term, there's this secular trend of an increase of 2 to 3 degrees Fahrenheit. Now this is Celsius here, so say 1.5 degrees Celsius temperature trend. More recently, we've had regular monitoring programs in the Bay that are measured temperature that are consistent with this. Here, a colleague of mine looked at the Landsat data, trying to interpret surface water temperature in the Bay on a more specific spatial scale, and actually showed a general trend of warming throughout the waters of the Bay, with some local areas warming faster than others. But overall, he and a student found out there was somewhere between a 0.05 to 0.1 degrees C per year increase of temperature in the Bay. This is not inconsistent with other areas around the world where they've been monitoring temperature over the long period of time. Sea level is rising. Dauphin Island. I heard you need to convince your mayor about that. So in this part of the world, you have what, a 2, 3? Brian was telling me what, 2.6 millimeter per year over the long run trend per year in sea level rise. Here in this region, we have a higher rate of sea level rise because of two factors. Well, mainly three factors. One is the fact that we're in an area that's subsiding as a result of the deflation of the bulge that existed below the glaciers during the Ice Age. So our part of the world and the crust is subsiding, adding to what's realized in a relative sea level rise case that might be measured by a tide gauge. Number one. Number two, there's also stronger and stronger evidence that in recent years we've had higher sea level rise because that may be driven by Gulf Stream slowdown. Again, Science this week, Nature papers, they came out this week on this issue of a slowdown of the Gulf Stream. Why does that affect sea level rise? Because that Gulf Stream that moves past our shore pulls a lot of water off the shelf. If its velocity, the amount of water flowing past us, around Cape Hatteras flowing past us, slows down, the force to pull that water up is less, so the water along the shoreline, along the East Coast, is higher. Thirdly, we have, particularly in this part of the Bay, the southern part of the Bay, a lot of groundwater abstraction. There were large pulp mills that used a lot of groundwater that actually have reduced the pore pressure of water, creating also an additional amount of subsidence over that. So down around Norfolk, you've got, which is now a poster child for recurrent flooding that you see in the streets there. We have something like 5 or more millimeters per year. So sea level is a reality that's taking place here. It's also because the longer term subsidence, of course, has existed for hundreds and thousands of years. Now there's clear evidence that the additional sea level rise has been increased by a factor of 3 from where it was, say, beginning of the 20th century, because of rise of the level of the ocean, of ocean sea level rise, which really didn't exist very much. It was very slow before the 19th century. So one of the things that I just meant to point out, that one of the other implications related to this eutrophication problem of sea level rise is what happens to tidal wetlands, the marshes. Because those marshes are very important in the Bay as sites for nutrient removal, either sedimentation or denitrification of the excess nitrogen. We've demonstrated that they're pretty effective in that case. Furthermore, if sea level rise causes a disintegration of these wetlands, there's a lot of organic matter that's stored in those wetland soils that's then added to the organic matter burden of the bay that helps deplete oxygen. But here's the controversy, because there are some scientists, here's picking the work of Matt Kerwin down at VIMS, who basically says if you look at it, yeah, the sea level rise is causing the marshes to erode, but what's happening is they're marching inland and replacing lowland forest. And that indeed is the case, as commonly you've seen. You might have some examples of like this here, of these ghost forests that you see here, where marshes have invaded territory previously occupied by pines. But it's not the case throughout the bay. You go higher in the bay, there's no place for the forest to retreat, because it's all higher elevation. It's not flat landscape. So the marshes will be squeezed, if you will, into a smaller and smaller area. This is something that's probably a factor in the longer run, rather than between now and 2025, which is when we have to do this. So the Chesapeake Bay Program, bless their hearts, good government agencies, federal and state, have a tremendous capacity to do management-oriented modeling, which I showed you some products for those bar charts which they estimate the nutrient loads. Those models are by which they determine by how much do we need to reduce the nitrogen and phosphorus loads to get the results. So they're really baked into the DNA of our whole science-based management scheme, to the point where people are very proud that these are kind of viewed as the world leaders of using these kinds of scientifically sophisticated, complex models of the atmosphere, the watershed, as well as the estuary. So they turn those models on and ask the question, is that would climate change make this worse, and by how much? So they used, with some expert consultation, projections, climate model projections, to say that between the base period, which was 1992 to 2000, to the year 2025, so a little up, let's say 30 years or so, what would be the increase in temperature, and came up with 1.1 degrees C. Again, not inconsistent with that actual observational record that we showed in that time period. And then what would be the increase in rainfall? Here they found problem in that climate models are really not very good at predicting precipitation very accurately. Why? Because they're global models and they don't take into account local, regional phenomena, like how much water is going to be evaporated right off here, off of your shores or in Mississippi Sound, and how does that affect the rainfall locally. So they used that, and they did it by these major watersheds. They had used the existing data, the historical data, 80-something year record, and then just projected those, extrapolated them to come up with a 3.1, and then played some games in terms of the intensity of rainfall and the like. Sea level also, they tried to use these sea level rise projections, and in the end fell back on the tide gauge record, the actual observational record, and then just extrapolated from there, assuming, in this case, in the end, from the mid-90s to 2025, about 0.17 meters of sea level rise. Now, earlier, when they were doing this, they were advised and they used a higher sea level rise rate of 0.3 meters during that period. And that becomes important for the reasons I'll tell you about. So, what did they conclude? They concluded that, these model estimates concluded that the delivery of nutrients, in this case I'm showing nitrogen again, here's nitrogen, here's phosphorus, actually would be fairly modest in terms of total nitrogen, about a 0.6% of an increase in load of nitrogen. Is that you'd think, was that much to worry about? But what they found, though, that the speciation of the nitrogen forms would change under climatic trend, such that there would be an disproportionate increase in dissolved organic nitrogen, nitrate, which is the most readily stimulatory of the forms, as opposed to organic nitrogen, which has to be degraded, and not all of it can be degraded and is less important in stimulating algal production. For phosphorus also, they actually found a decrease in phosphorus loads as a result of this model estimate. So they went from that, and then they projected on the basis of the bay, the hydrodynamic models in the bay, that this would increase the hypoxic volume of the bay, all other things being equal, by 2025 by 7%. So we would miss our goal that we were all striving for. If we did everything we said we were going to do in terms of reducing nutrient goals, we would still have 7% more hypoxic volume than we thought. And then from that, estimated that that would require 9 million pounds of nitrogen load reduction and 500,000 pounds of phosphorus reduction. Now, these numbers don't mean anything to you, but when the jurisdictions, the states, are struggling to get every pound, every million pounds is a lot, this is another burden. And mind you, this is by 2025, and they've got 7 years to get this done in addition to that. In addition to that, there are other new challenges they have to meet, because one of the major dams in the Susquehanna River is filled up, and it is exporting more of its nitrogen and phosphorus load to the bay. We got to account for population growth that's taken place and will be taking place in that time frame. So it's a big burden. The managers, and these are relatively speaking very technically sophisticated managers, up to the level of secretaries of agencies in these states who know a lot about nitrogen and dynamics and oxygen and all those things. They were, of course, taken aback, but they were also said, well, wait a minute, just 2 months ago you told us that it was going to be better than we thought, and now you've shifted that estimate, and now you're saying it's going to be a lot worse than we thought, and all you've done was shifted the estimate of the amount of sea level rise from 0.3 meters to 0.17 meters. So there was a wake-up call about uncertainty. And climate modelers, the climate community always deals with uncertainty and always deals with a range of projections, whereas these management models for water quality have been singular, have been deterministic, and now they're struggling to figure out how to bring this uncertainty into the equation. So what they decided to do, and this is like real time, this is like 2 weeks ago, they were concerned about this shift in projections. So at this time, they're not apportioning the additional load reductions to the states, as I indicated on that previous slide, on their watershed improvement plans, but will acknowledge, asking those states to acknowledge that they might have to increase their load reductions by that amount. And they are now on a forced march to address this issue of the scientific uncertainties. And by 2021, consider the load reductions that we have to put onto the legally required mandated reductions to meet the milestones that were agreed to. So this is interesting politics here. I've shown you a couple of these pictures I'm in, and I'll explain to you in a minute. So here we have the great state of Maryland, which I work in, has always been the leader of the bay restoration, always pushed the envelope, always pushed the curve. Why? Because we have most to gain from it. We have the most degraded part of the bay, but we can't do it alone. We're required on Pennsylvania in particular, but on Virginia. But we have now a Republican governor. In Maryland, even a Republican can't be against regulation if it's for the bay. So he is now sort of supporting this notion, and his Secretary of the Environment, a Republican governor, mind you, is just quoted as saying this: the science is not exact on this, but we also can't afford to wait for that perfect and mythical moment when all the science is perfect and everything is fully understood. We need to be proactive. If we contrast to that what's going on in the national counterpart, EPA, and Administrator Pruitt, saying the science is not in yet. There's still debate, so we're not taking action. So there's that interesting dynamic. This is me, by the way, and getting an award from Governor Hogan. I've worked with five governors, and I sit on the Governor's Bay Cabinet and have interacted quite personally with these governors. This governor, who's been in office for 3 years, this is the first time I'd met him. He's detached from it, but he still has to be supportive of this. This is, by the way, if you don't recognize him, Terry McAuliffe, who was the governor of Virginia, was Bill Clinton's campaign manager years ago. And here is an interesting character. I don't know if you recognize him. He's been in the news last year. This is Ralph Northam, the new governor of Virginia, who was supposed to be a tightly contested race. He won it overwhelmingly. I was at a forum with him on offshore oil and gas off of the East Coast, and my point that I was going to save to the end of this forum discussion was to say, you know, it's not about oil spills, it's not about your tourism. The real issue is, why should we be drilling for fossil fuels that might, if we found them, might come into play 30 years from now, when we have to be almost off of fossil fuels by 30 years. So I was waiting for my turn to make this point. The governor of Virginia made it for me. He said, this is ridiculous. Why are we drilling for fossil fuels? Almost stole the words from my mouth. And meanwhile, we have EPA Administrator Pruitt, who, when he was the Attorney General of Oklahoma, led a group of attorneys general to join the lawsuit with the Farm Bureau to stop the Chesapeake Bay TMDL. So here we have an EPA with an administrator who doesn't want to believe in climate change, but yet, on a practical level, it's driving the train on this climate change issue, and it's driving the train also on a regulatory response to the Clean Water Act for the Chesapeake water quality TMDL. So I think let me just quickly go through. Here's another analysis that other scientists, these are some scientists from VIMS, have done to address in a different way the same question. They use different models and so on. So the bottom line is that you see, they use a different time frame, 2050, is that from the base case, this was the 1985 case, we would see a significant reduction if we did this, met all the goals of nutrient reduction. Anoxia gets down close to zero. Hypoxia gets diminished. But if we add climate change to it, it reverses that to a certain degree. But the big factor is that it increases the volume of water that's not below 2 milligrams per liter, but between 2 and 3, between 3 and 4. So not technically by a defined boundary hypoxic, but the depleted oxygen conditions over a large volume of the bay. And that's actually shown here somewhat as well, showing that the area that's below 4 milligrams per liter really increases rather substantially, whereas the anoxic area decreases only minimally with their estimates of the climate change impacts, hypoxia a little bit more. And you can see here's the positive effect of sea level rise, diminishing the extent, percentage-wise, the extent of hypoxia, broken down by inflow. The inflow of more fresh water carrying more nutrients is here. The big factor, by their estimate, is temperature. The warming of the waters is the largest factor that would be driving lower oxygen levels in the bay in that time frame by 2025. So, in conclusion, the increasing temperature and the changes in the inflow that we expect, and they aren't the same all over the country. There are good reasons that why in the southeast actually the runoff might be diminished. It might be very concentrated with extreme rainfall events, but the total rainfall might actually go down based on some climate models. And the timing of that and the rising of sea levels will affect hypoxia in some ways that we have a general understanding of, but we don't know precisely. And it will require additional nutrient loads. So my thought about this, in terms of everyone focused on this 2025 date, is that the real challenge comes later, when we have to sustain the gains that we've made, improving water quality by the commitments we've already made, and then also also then deal with what the future of the rest of this century brings us in terms of a changing climate. So that we really need is not the plan to get us to 2025, but a plan actually that takes us beyond 2025, when we can accommodate the issues of changing climate to adapt and modify our efforts to achieve environmental benefits goals through this issue of nutrient pollution. We have a lot of time then to improve the role for scientists to play in this process to improve it, and we're going to be on a fast march over the next year or so to help move us in that direction. So I think that's all I have. Hopefully I've gone too long, John, but I'm happy to take questions if you have them.